Bismillahirrahmanirrahim. Greetings. In the previous video lecture that I uploaded about 3 days ago from the date of this video, I discussed about the one-to-one correspondence between the set of positive integers, the counting number, and the entire set of integers. At first it sounds like peculiar and counterintuitive, but seeing is believing. So we have already seen that. Now the contents of that video, of that lecture, is kind of pre-requirement, kind of preliminary for this video. So if you haven't watched that one yet, I strongly recommend you to watch that one, and I'm going to give the site link in the comment section. Now, in this video, I'm going to show that there is also one-to-one correspondence between the counting number and the set of rational numbers. That sounds like more kind of counterintuitive, more kind of absurd. But seeing is believing. Now, there is no deductive or inductive mathematical formula and analytical proof for that. It's only through the demonstration that was first introduced by Cantor about early 20th century. Now, in reality, historically, the idea was given by Galileo Galilei, 300-400 years before Cantor, in fact. That's good to know about the history, because history gives us some hint of seeking and finding something new. And of course, as I mentioned in the previous video, it was first rejected, his idea, but seeing is believing. Now, what we are trying to do, first of all, between 0 and 1 alone, between 0 and 1, there are infinitely many rational numbers, as we already know. And how can in the world count them? Because they are like water of ocean, they are connected to each other. And how can we put them into one-to-one correspondence with a set of positive integers? That is kind of we are going to show in this video. And again, seeing is believing. Now, the terminology and word that I will be using more often is about fraction to be numerator and denominator to be relatively prime. This word you will be hearing from me, so I have put it in writing. I'm going to zoom it so that you can read it and maybe make a note out of it so that the vocabulary is familiar with you. And also about the proper and improper fraction, I will be talking about that. Okay, then let me zoom that one for you and take a note of it before I officially start the lecture, if I may. Thank you. Okay, then let's see what we can do. Is that the strategy is to make a list, L-I-S-T, a list of the rational numbers. Once, if we succeed to put the rational number in a list, then we can start to count them. 1, 2, 3, 4, 5, and so on. So how can we put them in list? No, there is no order in the set of rational number. There is no number, we don't know, nobody knows what will be the next rational number next to half, or next to 1, or next to 3 half. Nobody knows. As I said, the set of rational number is condensed. There is no such a thing. So if there is the list that we are going to make, it put the rational numbers not in order. So one of them can be here, the other one can be 10 miles down somewhere. But the point is that we convince you that every rational number will be in that list. If we succeed that, then lo and behold, we have succeeded to show that that the set of rational number is countable. So now let's start to see how we can do that. I have put it in a kind of algorithm, if I'm pronouncing it correct. I still have problem with pronunciation. Algorithm, procedure. And I show you the procedure with, before I go to some examples. Now here I have written them large enough, I don't have to go back and forth and zoom in and zoom out. Now here, don't forget our point is to construct a list, L-I-S-T. Now here I put 2 consecutive integers. You know consecutive what the word means, one after the other one. So 1, 2, 3, 4, 5 and so on. So A and B are 2 consecutive integers, like 2 and 3, like 3 and 4. So I start with 1 over B, the one that is larger. Like 2 and 3 I start with 3, 3 and 4 I start with 4. So I start with 1 over B, that stays. Then I write the multiplicative inverse of that number. In this case it's B over 1. But B over 1 is same as B, so I don't have to write it. I wrote it for the sake of argument, but as you notice I have crossed it, which means there was no need. Then I go to 2 over B. You see, from 1 over B I go to 2 over B. Don't forget B is the larger of the 2 consecutive integers. And then next to that I write the improper of that fraction, which is B over 2. Comfortable so far? And continue this one up to B over B. But when I reach B over B is always born in every consecutive integer that I'm going to take, so there is no need to write B over B either. Alright, now I have an example for you. I have quite a few examples. Let's go from the 2 consecutive integers to be 3 and 4 to see how many rational numbers may land in this interval, in a sense, between 3 and 4. Now, we start with 1, 4. 1, 4 is always there, so we don't need, I didn't cross that. But 2 and 4, 2 over 4, 2 and 4 are not relatively prime. Because 2 numbers are relatively prime, numerator and denominator, if the only number that divides both of them is 1. So in this case, 2 over 4, 2 divides both of them. In this case, 2 over 4, which is 1/2, is somewhere in the list before that. More likely. And then, same goes with 4 over 2. 4 over 2 is what? They are not relatively prime, and then what? Is somewhere there. In this case will be 2, which is what? Which is 2 consecutive between 1 and 2, which is 2 is there. So I crossed it. Now 3, 4 and 4, 3, notice that I put circle on them. I did not cross them. 3, 4 and 4, 3, they are relatively prime. The numerator and denominator relatively prime, and more likely they are not in the list before them. So they stay. So in this list I have 1/4, 4/3, and 3/4, 4/3, and I don't have to worry about 4 over 4 because 4 over 4 is 1, but 4. So I have 3, 4 and these numbers between them. You follow that? Okay, now let's go for another example. I have quite more to come. Let's go from 4 to 5. 5 is a prime number. Therefore, 1, 2, 3, 4, when you put the numerator and denominator, they are all going to be relatively prime to 5. Is that right? So I start from 1/5. All of them I start. 1/5, I do not cancel it. I do not cross it. It stays. But 2/5, next to that, I write multiplicative inverse of that, which is 5/2. You see that? And these, they are relatively prime. More likely there is no fraction before them in the list. So same is true with 3/5 and 5/3, multiplicative inverse, and 5/4, and then 4/5, and then goes 5/5, that is 1, is already in the list. So those that are in the list, previously, I do not put them there. Are you with me so far? It's very, very interesting and kind of follows common sense. Now, let me go to, well, I don't need this one. Let me take it off. And let me go for another example I have for you. And this example also, I suppose you don't need I don't need to zoom it in and out, in that case. Now I'm going between 5 and 6. Between 5 and 6. Between 5 and 6, all the rational numbers I want to fill, I start from the bigger of the two consecutive integers, which is 6. I start from 1, 6. Next one is 2, 6, 3, 6, 4, 6, 5, 6, and each of them, next to them, what? Multiplicative inverse of them. Now, 2, 6, you see 2 and 6 are not relatively prime. They both are divisible by 2. Is that right? So I cross them. It is already in the list. What is this? It is 1/3. 1/3 is before that. I will show you when I put all of them in the table. Okay, same is true with 6/2, which is 3, is in the list before. So I cross them. I don't repeat the same number that is already in the list. And then only 2 of them left, and they are relatively prime to 6, which is 5, 6, and 6/5, and both of them stay. So that is another kind of observation. Okay, now let me see for another one, if I may. Again, I have put them large enough so that I don't have to zoom them for you. Now here is 0, 1, then 2, then 3, 4, 5, 6, and what will be the rational numbers that fall in this between these integers in this list. So 1/2, then multiplicative inverse of that is 2, then I start with 1/3, multiplicative inverse of that is 2/3, I put it, that, excuse me, is not multiplicative inverse, my apology. 1/3 multiplicative inverse of that is 3/1, but 3 is already there. Then 2/3 multiplicative inverse of that is 3/2. You see that? I wrote it. And same goes with 1/4 and so on and so forth. So you can take a zoom it for yourself bigger and write it down if you like. Okay, then let me see what else I have. For the 5 I did go. Now let me go to negatives. So then the question that you may ask is that, not so fast. You said that the set of all rational numbers. So where are the negative ones? Where are the negative numbers? You are always talking with the positive so far. So let's see how we can insert the negative rational numbers also in this list. Let's see how we can do that. Now, how we put them in this list is as follows. Next to previous list that I had, that list can go forever. Next to every positive member, every member on that list, put negative of that member. So next to 1, put -1. Next to 2, put -2. Next to half, put -half, and so on and so forth. So I have done that. You see that? 0, 1. Next to 1, I wrote -1. Next to 1/2, I wrote -1/2. Next to 2, -2. Next to 1/3, -1/3, and so on and so forth. Do you follow me? Now I claim that every rational number in the world, they are in this list, and this list of course goes forever. Here I stop at 5, but you can go to as many as you want. Do you follow me? So how could I prove this claim? How could I justify this claim? Now, in the previous video, I did talk about how to change rational numbers that they are given in the form of decimal to change it into the form of A over B form, fraction, so that we can show that. Because you say, okay, what about 0.333333? Where is that located? So we convert 0.3333 into A over B form, and then we look to see where it could be. So this one I have already done in the previous video lecture, and I repeat myself, I strongly encourage you to watch that video before this, and how to change this one into A over B form of it. So 0.333333, the A over B form of it is 1/3. Is that right? And where is that 1/3 located? Here it is, between 3 and 2. Then you say, okay, select one other number, select something randomly. Now, because the previous one was a preliminary for this, so I'm not going to show you how to do that, how to change decimal into A over B form. I have already done it. I just go over them and show it to you if I may. Okay, now you are asking me, tell me where 41.22222 is located in your list. Just some randomly I selected the number. Now I have already shown you how to change it into A over B form. The A over B form of it end up to be 371/9. Okay, it is improper fraction. So if the fraction is improper, the number that you find, rational number, convert it into proper by just interchanging the numerator and denominator. So when you change numerator and denominator, you get 9/371. Okay? When you get 9/371, you remember that we always took the bigger of the two consecutive integers, and then we started 1 over that, 2 over that, 3 over that, 4 over that, and so on and so forth, and the multiplicative inverse of them. And here we have 9/371. Therefore, this number, where does it fall? It falls between the bigger of the two consecutive integers to be 371, and the smaller one to be what? 370. So I know precisely where this number will land, but there is no order, remember. This, for example, 1/2 end up to be somewhere, should be between 0 and 1, but in our list is not between 0 and 1. We are just showing that, yes, we can show them, we can count them. Now going back to the, to this one that we can count, let me go it one more time if I may, is now that I can say I can count them. Count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and so on and so forth. You can do that forever. So every rational number will be in this set. Now, there are other ways to do that, of course, the list can be presented some other ways, and I may make another video to show it some other way to make your list and persuade the audience that yes, the set of rational number is countable. So I repeat myself again, the set of rational number is condensed. There is nobody knows what is one rational number after the other one. It's not like integers that we know 2 after 1 or 3 after 2. And we know the neighbor of 2 to be 1 and 3, but we do not know what is the neighbor of a rational number, non-integer rational number. Nobody knows. But this method, he shows you that you can count them. Now the interesting part is that the set of real numbers you cannot count. And I may make also a video about that one. It's in the YouTube almost, it's very popular. Okay then, if I may, I want to put the history of that for you, and I don't have anything else left, I suppose. Okay, then let me put the history, zooming in for you, so that if you like to take a note or just read it for yourself. This one first, yes. Thank you. Okay, now next, let me put the next one. The next one, I don't have to zoom in, is already zoomed. And I wait a few seconds so that you can take a note or read it and then go back. Okay then, the presentation of this lecture is to the level of a junior high school or high school student, and a good grade school student that they are curious, very easily they can comprehend this idea. And I strongly recommend you, if you have younger brother or sister, or if you have younger children, to go over them and show that, because you are improving their critical thinking, the analytical thinking, so you're doing them a great favor so that they can see beyond the horizon. And the kids are they're like a sponge. They are very, they absorb quickly, and they love to hear things like that. Especially the younger they are more curious to learn something new. So I do strongly recommend you to discuss this one and present it to your kids, to your brothers and sisters. Okay then, I thank you for watching. I wish you all prosperity and good health, and please stay safe. So long.